Our next speaker is Ingmar Posner. Professor Ingmar Posner leads the Applied Artificial Intelligence Lab at Oxford University. He serves as Deputy Director of the Oxford Robotics Institute, which he co-founded. He's also a co-founder of Robotica, which you may have seen at ICRA. And Ingmar has an impressive track record in addressing key challenges in robot learning. So we are really looking forward to his keen insights today. Thank you.
Awesome. You got it?
Okay, great. Yeah.
Wonderful. All right. Melissa, everyone, thank you so much for inviting me. It's a real shame I can't be there in person. It's of course a pleasure to be invited. And today I would like to talk a little bit about sort of learning to simulate. And this sort of talk comes almost in sort of four parts. One is sort of a fairly general statement that I like making at these sort of meetings when we talk about robots in the wild. And then I'll do something potentially fairly obvious, and then I'll take it to a place which I think you might find less obvious. All right. So let's get started with sort of the fairly obvious bit in the beginning. So we're all excited about robots in the wild, which is great because we're roboticists. And every couple of years, I get the opportunity to sort of speak at a meeting like this, where we talk about what does it take to get these robots out into the real world, etc. And the thing that I come back to is robotics is fundamentally a systems challenge, right? Ultimately, we have systems that we want to push out there, we want them to do stuff, and that needs to happen sort of robustly. They need to be auditable, safely, and so on. And particularly when it comes to things like productizing or operating amongst humans in the real world and so on, that is really, really quite important. Now, I'm also super excited about machine intelligence and machine learning in general. And so the question is, where does that fit in, right? And the interesting thing here is that ultimately the challenging stuff is actually the systems part, right? So as roboticists, particularly with the field robotics head on, developing the systems that actually wrap the AI modules for autonomy is really, really hard. Particularly because, as I said before, we want them to be versatile, we want them to be auditable, introspective, designed for safety, and so on. So that's the systems part of it. But the AI side of it is really quite important as well. And that, like if there is such a thing as AI systems, it's very much about the AI hygiene part, right? That's crucial. Deployment solutions do need to be efficient in computation, they need to be efficient in energy, they need to be efficient in data. And what that boils down to ultimately is that, robotics is actually a key driver for AI innovation in that space and beyond. And that's really, really important. It's not just an addendum. And I would love for everybody here to internalize that, because the questions that we're asking here are really, really relevant, not just in robotics, but also the other way into AI and machine learning. Okay, so where does machine learning actually fit? Generally speaking, there's sort of, from the system side, there's sort of two places where it can fit. And first one is improving the platform, which is what many of us talk about very often, right? So we might improve the sensor performance, for example, fusing them with other modalities and so on. Situational awareness, Davide has just given a very nice talk about perception, prediction, behavior planning, and so on, which is great. And until not that long ago, this bit was often sort of ignored almost, right? So there's also the off-board part where we actually just talk about improving the tooling. And there we talk about things like automatic or synthetic data generation, versatile simulation, et cetera, et cetera. And then, of course, we talk about the sim to real gap, but what about the real to sim gap, right? So with that, actually, what I mean is, imagine your robot stands or is encountering a particular situation. Wouldn't it be awesome if you could somehow directly translate from that situation into a simulator where you could just try some stuff out, right? That is actually a fairly relevant problem, and I'll talk about that in a little bit. Then there's things like third-party behavior estimation and so on and so on. And so for the rest of this talk, I would like to talk about three of these things. The first one is going to be about synthetic data generation. Then we'll talk about the real to sim thing a bit. And then I'll talk about planning. All right. Before that, though, let me just briefly say one of my favorite things, which presumably many people would have heard before, if not from me, then from other people. What has machine learning actually brought us, right? So as field roboticists, what we can do now is accurately learn some pretty complex mappings, right? We've got long gone beyond cats and dogs, which is delightful. But also we can execute these mappings very quickly indeed. And again, I wish Davide and I haven't coordinated this, but I think he gave a great intro because this kind of makes that point exactly, right? So there are things that we know how to do now very swiftly because we can literally distill this knowledge into a learned model, right? And of course, he said many more interesting things than that. Also around how we, for example, bridge the sim to real gap by learning what the differences essentially are between the simulator and reality, right? And so that's also super relevant and very interesting. I'm not going to go there because he's already done that. But the challenge with deep learning is that it has a data problem, right? Twofold. One, it needs lots and lots and lots of it. And secondly, of course, somehow we need all the long tail cases that are relevant to us, right? And so there are a bunch of ways we can address this, particularly as field roboticists. One thing that I've talked about lots before, so I'm not going to spend much time on this now, is system level self-supervision. And that's really helped us in sort of our deployment, particularly on the perception side, quite a lot, right? So think about this as your robot is not actually being deployed. Right now, for example, this vehicle is being driven by a human, right? And because all of the systems engineering that's gone into it, you can exactly, you record the data, you know exactly where the wheels are, you know where the track's going, and so on. And on the training vehicle, you have a sensor that tells you where stuff is, right? The details of that aren't necessarily important right now. The important bit is that afterwards, you can actually use that information to automatically generate training data that, for example, allows you to come up with masks like the ones you see on the left here, that you can then throw your favorite segmentation algorithm or your favorite model at. Like we did back in sort of 2016, I think it was. And what you end up with is a trained model that you can deploy on a single mono camera that basically tells you where a human would drive in this particular environment. And all of that kind of comes for free because the training data is generated by the system, not by anybody clicking on anything. And if you kind of put on that hat, other things suddenly become possible. Like the thing on the right here, where you talk about distractor prediction. So imagine that you have a visual odometry system and you would like to know which key points you can and cannot trust, right? What we've done here is basically exploited the fact that we operate in the same types of environment, and particularly also in the same environment as most of our robots tend to do, right? And we can then say, well, how does the environment change every hour or whatever cadence your robot is operating at over the space of, you know, n days, months, whatever, right? And then you can say, well, what changes? And from that, you can distill out, for example, masks, like the ones that you see on the left, that you can then regress onto from your sort of image input, right? And so what that means is that without ever telling the system about cyclists or cars or anything like that, all we've done here, all the system has done is learn about things that are probably not very useful when it comes to visual odometry, or conversely, things that are likely to be moving in your environment, okay? Okay, so that's sort of the point for system level self-supervision. This whole thing also works on the navigation side, particularly also nicely when it comes to dealing with awkward sensors like radar, and we'll hear more about that in a second. So for example, you can imagine that you have an awkward sensor like radar, like you have on the left here, and during training, you supervise that thing with a much more amenable, potentially more expensive, potentially, you know, very robust navigation source, so pose source, right? And if you do it right, the effect that will have is that you will learn a representation in your radar embedding that only focuses on parts of the data that are relevant for navigation, like you see in the middle here, right? And so the effect of that is, again, in a completely free of manual labeling sort of way, you end up with a system that is a navigation system that operates on radar only, that is accurate at city scale, open loop sort of pose estimation. Okay, again, a way of doing system level self-supervision. So I've spent lots and lots of time on this in the past, so I'm not going to talk about that more. One thing that I and my group are currently very excited about and have been for the past sort of 3-4 years now is a particular mapping that is now open to us, which is deep generative models, right? And particularly the fact that we can use them for unsupervised learning. And as many of you will probably know, there's sort of two flavors of that out there that people often use. There's more than two, but so these are the ones most people are familiar with. So we've got variational autoencoders on the left here and generative adversarial networks, GANs, which are similar in spirit, but different in sort of exactly what they do and how you train them. And we'll talk about that in a second. But I'm now going to go do something very obvious, which is generate some data with a GAN. And then we're going to come back and do some interesting stuff with a VAE. Okay, so the first chunk of this is really about synthesizing challenging sensor data. And you know, we've heard about deepfakes. We've heard you know, lots of published papers recently around generating data for autonomous driving when it comes to vision-based data and so on and so on. But what about something that is really, really quite horrible to deal with, like radar? Now, if I was in the room, I'd ask you for a show of hands as to how many people here have actually worked with radar. If you have, you will probably not like it very much for all the reasons that are on the screen right now, okay? It's really, really horrible. Images are nice, point clouds are great. With radar, you've got the issue that, when you see something that's dark, it doesn't necessarily mean it's occluded, and it doesn't necessarily mean it's free. When you see something that's white, it doesn't mean that it's occluded or free. You get these sort of really horrible saturations. You get multipath reflections, like these ghost reflections here, and this is why I'm hoping that you can see my mouse. Okay. And you get sort of a lot of speckle noise as you zoom in, and then you also get these tiny little blobs here on the right, which are the things that you care about, like cars, for example, right? And not only is it tricky to operate with this, it's also very hard to get labels for this, not just because of the amount of data you need to get labeled, but because it's really difficult to deal with, even for humans, right? So there's a lot of unpleasantness. Now, wouldn't it be nice if we could throw something like, if we could set up some scenes in a simulator and literally just end up with simulated radar data so we can label everything that's in there. And that is something that we've done last year, where we basically operate, this basically works with any simulator, but we've operated off Kala to then say, okay, well, we can actually generate realistic, in some sense, I'll say more about that in a second, radar data from the scenes that we get out there. And that is actually an immensely useful thing. Now, unsurprisingly, how do we do that? Going back to a point that Davide made earlier about input representations, here we've actually chosen to work with an elevation map. It sounds old school, but we've done that simply because it is the single thing you can get out of almost any simulator, right? So we have an elevation map from a simulator. And on the other hand, we have, of course, real-world radar data, of which there is more around now. But we do have something else, which is basically laser data, but you can also think of that as a partial elevation map. Okay, and the nice thing between the real radar and the partial elevation is they're aligned, whereas, of course, the simulated elevation is not aligned at all. And for those of you who are into this, of course, now that I'm starting to talk about non-aligned data, I'm going to start talking about using a gun kind of approach, which is great, of course. And so we can, for example, start by taking the simulated elevation map and learn the forward model to a simulated radar scene, right? We can ground that via GAN, via discriminator, against the real radar. So this guy here, the discriminator there, basically aligns the distributions between the simulated and the real world data, which is great. Additionally to that, we can then actually also go the other way, which is we do that because we can, but also because it's useful, where we basically saying, okay, I'd like to learn the inverse model as well. I'd like to learn how we get an elevation map from a radar scan. And it's useful because we can introduce another constraint, which basically is a discriminator between the simulated elevation and the real predicted elevation. So that gives us another constraint for this. And the number of constraints here becomes important because of the complexity of the data, okay? And then we can go further than that because we can now actually introduce the cycle GAN parts. In fact, what we're doing is run two cycle GANs in parallel. One to look at the elevation at the top and one to look at the sort of the radar at the bottom. And then the sort of cherry on the cake is we can actually ground the predicted elevations in the partial elevation readings, right? The laser scans, which is sort of the M star that you see there, right? So these are all the losses that we eventually can put our hands on without actually having to expend any effort in sort of labeling anything. And you may well ask, why on earth do we care about all of these things? And the answer is we care about all of these things because radar data is so complex that we need all of that in order to tie it down. And I'm not going to spend any time on quantitative results in any sort of way or form other than saying that in the paper, if you're interested, there is an ablation. And that ablation is basically looking at how many of these losses we actually need in order to perform well. And what you see here are basically the outputs of or the outcomes of a real world test set to which we apply a model that is purely trained in simulation. And it turns out with all of these losses, we can actually do really quite well on a segmentation task. On a more practical level, of course, what we get out is something where we can map directly from simulating an elevation map into radar data, which is neat. But of course, we can also go the other way around, right? So we can start with a real world radar data, and we can immediately map that to an elevation map. Okay, so much for the sort of fairly obvious GAN part. But now let's talk about the next bit, which is sort of the learning and the mental model part in an unsupervised way. And again, Davide has given a great introduction here because he's already talked about different ways of, or the traditional ways that we've used in order to sort of think about perception and action, particularly the pipelining of discrete components like the detect, plan, control, and so on, and what that takes. But where does that fit into the narrative, this notion of perception and action and generative modeling? Now, it turns out that in 2018, Hans Schmidhuber published a paper called World Models. And that is actually super exciting for a number of reasons. Mainly because it's about predicting the evolution of the world with a model that is purely learned from observation and interaction. And typically that's a generative model, right? So you're saying, actually, I would like to generate what the world looks like in the future. And that's really interesting because they've shown that you can actually, to some degree, start to train agents to perform particular tasks in those sort of environments. And in the early days, they were pretty simple tasks, granted, but nevertheless, that's a really, really tantalizing thing because there's a vision piece that I would really like you to onboard here. Imagine a world where your robot is facing the environment that, or the particular situation that you wanted to deal with, and it's able to immediately ground the situation, or the environment and everything in it, into sort of a symbolic representation, a mental model of the world, a world model that you can then, that it can then not only ground the symbols in, but also things like try out the action that it's proposing and predict what happens next. Or in fact, even perform some introspection to say, does it work well, does it not work well, or even acquire a new skill, right? So that's sort of the tantalizing promise of what we're after here. And there are different refinements of this, of course. You know, some people have looked at this in the past that. So in terms of introducing the structure into those latent spaces based on control assumptions, planning mechanisms, disentanglement, and we've also been very, very active in that space. And while everybody's made progress, there's still some things that are fundamentally missing, right? The first one is robust reasoning of sort of relevant entities, things like objects, coherent and consistent generation, prediction to some degree. A lot of good stuff has happened there, but you know, we're still not quite there. And here's a really big one: application to real-world data and systems, and that's something that that MALAB is certainly pushing quite hard as well. And so, just to give you a flavor of where this is headed, one thing that we're excited about is a particular type of structure that that introduces sort of object-centric operation. So object-centric generative models, right? Why do we care about those? Because reasoning over pixels is pretty enough, right? Because it ignores a lot of the structure. We clearly want to explain the world through objects because it does reduce the number of possibilities, right? The number of possible observations that we could encounter. And then, of course, if we consider object interactions, we immediately get into things like behavior, physicality, and so on. And the tantalizing part here is that we can actually, there is a path that allows us to do this in a completely unsupervised way. What you're seeing on the right here is one of the models that we've pushed out last year, where we basically take video input in and in an unsupervised way learn about the objects, learn about the segmentations, and so on. Now, these generative models, they're not magic, right? In fact, you know, if you've ever seen EM, you'll recognize some of this. It's basically a latent variable model where you're saying every pixel is explained by a latent variable, and you can group these latent variables into, for example, you know, a number of objects and a background, say, and you could even introduce some more structure into those and say for every object, I'd like these latent variables to be describing where it is, to be describing what it is, or what its appearance is, and so on. And then typically we assume that these object latents are independent, which is a pretty dumb assumption. And you know, we've done some different stuff as well, but that's, you know, it's one way of making our lives easier. And this slide is about, let's say about 8 months out of date, but it gives you a sense that it's getting busy out there, right? So that there's really some stuff happening, which is really interesting to see. But the typical design decisions that we're thinking about here is things like, how do we structure the latent factorization, right? So like, do we care about whether something's present, right? Or do we not? It can be useful for downstream tasks. It can be detrimental for inference, right? Do we care about getting a pixel-wise segmentation, or just sort of spatial attention like a bounding box? Do we care about parallel versus sequential, which is actually, it's a red herring. That's a bit of a wrong question. Actually, the question is, do we care about having to impose an ordering or not? And then there are things like scene versus video information, and as of late, also 2D versus 3D representations, and so on. But here's why some of that is also nice, even on the representation side, because if you do have a factorization of where, what, present, and so on, like the Apex model does, and a number of the models before that as well, it turns out that you can actually do some fairly useful thing just by observing the world. So for example, here, this is sort of a rearrangement task in simulation where the object matching is simply done based on the latent representation that's been learned for the appearance of the objects, right? So take the goal scene, run your model on it, so that will automatically segment it and say these are the objects, and this is what they look like, and this is where they are. And on the execution side, you basically do the same thing, and you then have a controller that that basically rearranges the object. So it's not rocket science, but it's a very, very tantalizing thing. And unfortunately, we don't have a video of this right now, but we have used this model in the real world on sort of similar sort of scenes, and we're seeing some fairly interesting stuff, and I hope to be able to tell you more about that in the very, very near future. Okay, last part. I would like to invite you to think slightly differently about how we plan. And particularly, I would like to think about that in the context of learning a statistical model of observed robot capability. And if you're thinking, what the hell does that mean? Then bear with me for another sort of 2 or 3 minutes. So imagine that you've got a robot manipulator, okay? And imagine that thing does motor babbling, and every now and then you press record and you get you literally get a snapshot of a pose, and that pose is valid, right? It's not in self-collision, it's just a valid sort of pose. And you collect a whole bunch of those, which gives you a data set. And then you essentially perform density estimation. Okay, so in this case, you train a VAE, which gives you a sort of a density model. It's an explicit density model with a latent space in the middle. And you basically train it by trying to predict the joint angles and the end effector position in Cartesian. There's a reason why you do that. We don't have to go into that right now. It makes the mapping a little bit easier. But the effect that you've got with this is that in principle, you're actually learning a forward and an inverse kinematic model. Okay. Now, you end up with a latent space that is in some way structured, and that's the thing that we're really interested in, the structure part of it. And you're going to hook up to this latent space, basically a performance predictor. In this case, it's going to be a collision classifier. So that thing takes in an environment feature, or an environment, or an environment encoding, or as in this case, just a single obstacle location, right? And all it does is it takes that and it takes your Z variable, so your latent variable, and says, am I in collision? And the beauty of that is you can actually use this via a process called activation maximization. Think of this as backpropagating into the latent space in this case, right? So you can backprop into the latent space, which basically optimizes in the latent space until you're no longer in collision. So in a way, what you've got here is a way of framing a constraint and performing constraint optimization in the latent space, okay? And it's a really cheap way of doing it for a number of reasons. One, anything that you can train a classifier for or predictor for, you can do that with, so it's super versatile. And the other thing is, because gradients add, you can sum as many of these constraints as you possibly want, and the framework is exactly the same. Now, what that means then is we can run this activation maximization with basically three losses. The first one is my estimated end effector. How close is that to the target? That's the sort of the green one here. I'm sort of still working on the assumption you can see my mouse. Then the last one, the red one, is basically the sum over all the constraints, all the constraint classifiers that you might have, right? The blue one here is super interesting because what the blue one says, it operates on the prior, and it says, well, okay, so you can walk around the latent space to your heart's content, but I want you to stick near the training data, near the prior of the data that you've seen. And that's why a probabilistic model or generative model of this is really super useful, okay? What is the effect? What does that look like? Well, when we basically take a walk through latent space, we end up with a smooth plan. And that's purely because of the structure in the latent space and the sort of smoothness priors that we put over there in terms of the prior structure that we impose and so on. But you end up with a smooth trajectory in latent space. And not only that, when we try this, we often find that, or in fact, we always find that this is kinematically and dynamically feasible, right? It's in fact commensurate in terms of execution time, success rate, and so on, and sometimes even better than many of the standard planners that we've got, right? Which is pretty extraordinary, given that we haven't planned. Literally, all we did was done some density estimation, okay? And the prior loss is kind of cool in this context because if you take the left, there's no prior loss, and you kind of get stuck in some really sticky places, right? Particularly because of the kinematics of the robot. But with a prior loss, because you're staying in areas where you're comfortable that you're kind of close to valid configurations, you manage to get your way out of those, right? And that's sort of an interesting use, I felt, of a probabilistic model. And because this is done in state space, it sort of immediately translates to a robot. So that's not a deal. Now imagine that you take not one arm but 4 arms, you attach them to a base, you turn them around, you call the thing a quadruped, okay? And then you manipulate the Earth. So Interestingly, and honestly, I never thought this would work. This was sort of a crazy idea from the beginning, but it does. The same thing works in order to get a quadruped to operate, right? So if you if you just send a quadruped into the Alps, then this isn't going to blow you away. Apart from the fact maybe that this is such a simple way of doing it, that this works is sort of odd in the first place, right? So again, we only train it on stances. Those stances have an encoding, and there's some cheating going on in this particular slide, in the sense that these are gray code encodings. So what you see on the right here is a projection of the latent space, which is ordered, which is colored by stance. And because the stances are gray code one hot encoded, the stances are next to each other. And what that means is that we can use a performance predictor. To literally as a carrot that says, now go to this stance, now go to this stance, now go to this stance, in order to effect a gate cycle. Okay, and it turns out that this actually works. Interesting thing, the other performance predictor that we use, the other constraint, is stability. So at every point in time, we run the current pose of the robot through a stability predictor, stability classifier, and the walk through the latent space is constrained by whatever you do, you must stay stable according to your classifier. Okay. Now, very last bit, throw away most of the stuff that I just said, forget the performance predictor for a second, replace the stances with an input of sequences from like a particular gate with very, very narrow parameterization, right? So you only look at a very, very narrow set of sort of gate samples, right? A bunch of things happen. The first one is the structure that I just showed you is no longer encoded in gray code, it just emerges, which makes a lot of sense, right? Because you're kind of seeing sequences. But then what you're doing now is you're predicting basically future plans of what you would like the pose of the robot to be as well, okay? And that's sort of neat, because what that means is you can do very quick online planning. And again, this is just a statistical model of what's going on, right? We haven't done anything fancy here. This is nothing, we're not sort of, well, I'm certainly not a quadruped person, right? But the interesting thing here is that the robot manages to not just repeat or execute the gate that it's seen, the parameters that it's seen, but because of the structure of the latent space, it can smoothly interpolate between gate parameters. So it can smoothly vary the gate parameters. And that's because of the disentanglement that we see in the latent space. So we can do things like change the cadence of the steps on the fly, simply by changing the drive signal. Okay, one drive signal controls the whole thing. We can change the foot height simply by changing that. We can change a whole bunch of other stuff. We can remote control the robot around. It's pretty cool. But if you think about the prior loss that I talked about a second ago, we can do the same trick here, because it's still a probabilistic model of what's going on. So when somebody pushes the robot, the system can detect when it's out of distribution, and you can change the behavior. And in this case, all we've done is taken some inspiration from the human literature, where basically, when you push somebody, the person will start stepping more quickly. This is exactly what the robot does, and it massively broadens. It significantly broadens the envelope under which the robot can operate. So not only can interpolate between all this sort of stuff, but this is shaping up to be a really, really quite a robust controller, given that it's not actually a planar controller of any shape that you've ever heard of before, right? So that was super surprising, and we've got some new results coming out in a few weeks on this, and that's certainly something we're super excited about. All of that is part of a big grant that we've got going on from Sense into Collaboration. So if you're interested in working on any of that stuff, do get in touch. I'm always happy to chat. And that is basically it. So learning to simulate, it's a challenge and it is an opportunity, both in terms of synthesizing realistic data. Many people are on that, but it can be quite complex, as I've just shown with the radar data. This unsupervised object-centric world models vision, idea, thinking is coming, and it's going to be glorious. And I very much believe that is something we should be exploring. And so a lot of my lab is currently very excited about that, which is great. And then, generative approaches, the power that we have with them these days really allow us to learn some data-driven models of complex systems in a way that I didn't really think was possible. And it turns out it is. And so I wonder where that is going to take us. All right. Thank you very much to my group, of course. Thank you very much to the organizers for inviting me, all our program grant partners, as well as some of our sponsors. And that is it. Thank you.